welcome to this lesson on valence shell electron pair repulsion theory, more commonly known as Vesper theory. Uh, it is a part of your AP Chemistry syllabus, Unit 2, and to go ahead with this, we are assuming that certain things from Unit 1, that is the octet rule, the distribution of electron in an atom, various cells, and the periodic table and the covalent bond formation by bond sharing. These things, the basic idea we have already, and then we can dive into this. So once we are thorough with this, the use of this in your AP Chemistry exam is not only this will help you do the molecular geometry questions, this will also help you do the polarity and the bond angle and the solubility questions. So very good topic as far as the AP Chemistry exam is concerned. So let's go straight ahead and break this by phrases. So valence shell. What is valence shell? What do we mean here by valence shell? So keeping some real examples of these molecules here. So when we see this, even if the geometry is not clear to us straight away, we know that the carbon must be in the middle, and here the phosphorus and nitrogen, coincidentally whatever it is written firstly. But what if you encounter something like this? Now we don't know these X's are directly attached to B or A, and which one is the central atom. In these cases, we follow these two rules. We'll see which can make the highest number of bonds. That of course we'll know by seeing the number of electron it has for sharing, and also the least electronegative atom among these will be the central atom. If we have confusion in the first point, let's just refresh our memory that electronegativity increases this way and this way. So if we are having some confusion here, if we have something like this, let's see, if we have something like this, so in that case, if we have this, in that case, between this and this, iodine is the least negative, so that will be the central atom. Alright, so going back, for now, for the first part, we have broken Vesper in 3 parts: valence shell, and then we'll do electron pair, and then we'll do repulsion. So for these, we are just picturing the valence shell for now, that how many valence electron will be there in the valence shell of these. If we are struggling with this, what number of that electron that I'm representing by crosses. So let's just see, refreshing our memory on how do we see the periodic table. So if we are here on carbon, so we go ahead counting like this: 1, 2, 3, and 4. So this is for the 4 electron I have put there. Nitrogen and phosphorus will have the same because they are in the same column, same period. So they will be like it goes 1, 2, 3, 4, 5. And chlorine, of course, is 5, 6, 7. Also, all the halogens, they just have one sort of octet. So, that way also we can remember it will be 7. So, once we have this picture of valence shell, we can go ahead and count how many electron pair. So, we will be taking the same examples for the sake of simplicity. So, that's what we did last time. Let's go ahead and do the valence shell for all of these. The top two examples and the bottom two, they have a fundamental difference in them, which we will see in just a moment. Okay. Now, these are the atoms which are not central, peripheral atoms. Which I'm showing by another color. Okay, here goes. So this is what we were talking about. The bottom two, they have this difference. Okay. Now 3 fluorine. I'm putting them in like this. Okay, all right. So we're done with valence shell. We are going ahead with the electron pair. In octet rule, hydrogen, the first shell, if it needs just 2 electrons, and it will be filled. So here we are making all the peripheral atoms happy first. So we gave hydrogen 2 and we gave chlorine 8. Now, okay, let's dive into what's different between the top two and the bottom two. Here, how many pairs do we have? We have 4 pairs. That is, all 4 of them are bonded, 4 bond pairs. Same goes for this one, 5 pairs, and all 5 of them are 5 bond pairs. Now, here we do have 3 bond pair for 3 hydrogens, but we have another pair which is a lone pair, or sometimes we also call it as non-bonding pair. And here also 3 bond pair, and how many of lone pair? 2 lone pair. Now the total here will be 4 pairs and 5 pairs. Okay, so looking at our examples, they have 4, 5 pairs, but their geometry will be greatly affected by the fact whether or not they have lone pairs, which we will see in a minute. Now, picture their valence shell again. They have these electron pairs around them. So electrons are nothing but negatively charged clouds. This cloud is called electron orbit. So these orbits, these 4 or 5 pairs, they have this similar energy, like the same poles of magnet. So what happens when you try to bring the north poles of two magnets together? They repel, and the repulsion will happen between these pairs also, because they are all negatively charged. So repulsion, how, due to the repulsion, they will try to arrange themselves in the 3 dimension. Here it is a balloon analogy. So here, looking something like this, it will be, if there are 2 pairs, this is for 3 and this is for 4. Whatever type of geometry will give it the optimal separation in 3 dimension for the given number of pairs, electron pairs, that will be assumed by that molecule. Now once again, if there are 2 pairs, so if there are 2 pairs, what kind of geometry will be there? So here, now these examples are they have something, some fundamental difference in them, apart even though they have 3 atoms each. So how do we proceed? We make process like we did last time, and like we said, octet rule is very important here. We know that oxygen needs not 1 but 2, so it will not be a single bond, it will be a double bond here and here. So now there is no lone pair and 2 bond pair. Now to arrange something for maximum optimal separation in a 360-degree space, there are these 2 ends, so it will be 180-degree alignment, and this will be linear geometry. So can we go ahead and say water will also have a linear geometry? This remains to be seen. 6 in oxygen. Let's put 1 hydrogen here, 1 hydrogen here, and okay. This hydrogen is happy. Okay, but what is different this time is we have this lone pair here and this lone pair here. So what do we have? We have 2 lone pair and 2 bond pair. So we don't have 2 pairs to arrange in a 360-degree space. We have 4 pairs and we need to arrange it in 360-degree space. So for 4 balloons, this right here, this tetrahedral stuff will be used. So how do we do it? Oxygen, hydrogen, hydrogen, lone pair, and lone pair. This is roughly, I have tried to make a tetrahedral geometry. Now In a tetrahedral, all of these are identical, so you can swap positions and put bond pair, lone pair, anything, anywhere. But later on we'll see that what happens if it is not the case. Okay, so moving on, this will also have the same thing, where one of the examples has a lone pair and another one doesn't. So in this case, 3 pairs to arrange, and 3 of them are bond pairs. In this case, even though 3 bond pair plus 1 lone pair, like we saw last time, 1 lone pair. So total is 4 pairs, and 4 pairs, like we saw, will be arranged in a tetrahedral geometry only. So when we do this thing with carbon, again, we know that there's 4 hydrogen, and okay, so 4 bond pair again, and plus no lone pair, in just the arrangement like 4 balloons, tetrahedral. Okay, now to make some space for the next one, so can we assume it to be same? We know that it is xenon is a noble gas, so it will be something like this. Let's see. This. Okay. Now, here, let's make 4 bond pairs for xenon. And 4 bond pair plus 2 lone pair. Now the total is 6. There are 6 pairs. So 6 pairs we cannot arrange in the tetrahedral geometry. If we are arranging 6 pairs in some geometry, and all of them have to be in the same in the maximum separation from each other, so the geometry will be something like this, where this is supposed to be a square planar thing. This is a square, and this is on, if it is in x and y axis, then at the top and bottom in the z axis, we will have total of 1, 2, 3, 4, 5 and 6 atoms. This is octahedral geometry. A clearer picture you can see here. This. So you see this 1 and 2 have 90-degree separation, and this 5 and 6 have 180-degree separation. So now, which one do we put in the 90-degree separation, and which one do we put in 180-degree separation? That will be it will be clear by the shape here. You see this shape right here. These two nucleus, and this is the shape of bonding electron pair, and this is the shape of non-bonding. This is kind of fat and squeezed. one way. So whenever we have a non-bonding pair, so that needs a lot of space to just fit in somewhere. So if all the places are not identical, and so in that case we will put it somewhere so it has the maximum separation from the other pairs. So we also have this this trick we can remember for the repulsion. If we have two lone pairs and there is repulsion between them, that repulsion will be greater than a lone pair and a bond pair, and two bond pairs, they will have repulsion, but that will be the least. So this is the order. If there are two lone pair, you have to put them in the locations where they have the maximum separation. Like in the octahedral geometry, we are looking at the 180-degree separation here. So up till here, up till this point, you see it doesn't make a difference because these positions are it doesn't matter if you put the lone pair here or here or here. I mean A, B, C, everything is identical. Here also A, B, C, D is identical. The only difference it will make is the angle here is 109.5. If there is a lone pair, it is kind of fat. So all these three thin people, suppose it is ammonia, so they will be squeezed in kind of. So instead of 109.7, it will be 107 or even lesser something. So but the point remains that they are identical, and you don't have to make a choice about where to put the lone pair. The choice starts from here, because one of the angles here is 90 and here it is 120. So 120 would mean more separation. So lone pair has to be kept here only. See, this is one option. If you have two, you put them here. If you have three, you put them here. But in none of the scenario, we have kept the lone pair in the 90-degree separation. So this is the scope of a mistake in your practice problems and even in the exams. So here also, in the case of one, all the 6 positions of course are identical, but in case of two, you have to put them like this. You cannot put them at 1 and 2. You cannot do that, because then there will be 90-degree separation. So this is tricky about the trigonal bipyramidal and the octahedral. Now, if there is a question about the bond angles, so like we said, squeezed in. So if there is the lone pair here, the bond angle is squeezed in like this, and even more the series we did was like the lone pair repulsion is more than lone pair bond pair repulsion, and which is more than bond pair repulsion. So since there is a lone pair repulsion now, the bond pair will be forced to come together even though there was repulsion between them. And so the angle is from 109.5, it goes to first 104.5, which is in water you'll see, and even more in sorry 10 it will go first to 107 and then it goes to 104.5. Here also, by increasing the number of lone pair, you see that the angle, how it changes. So this will come handy in some of your questions about the change in bond angle. Now your AP Chemistry syllabus and the official website suggests this to do some simulations, and here, since you are done with the theory, you can go ahead and add lone pairs and how the chemistry changes. You can rotate this, you can see the bond angles for yourself, and you can also see some real molecules here, and the exercise which we did in different type of molecules. Even in some of the practice questions, it will show you the actual angle, which is 107.8, but in the perfect tetrahedral it was 109. But since now there is a lone pair introduced, this fat guy has squeezed the thin people in, so now that is lesser than 109. So all kind of geometries you can see here, and you can, even when you are done with the real molecules given, you can go ahead and make your own molecules by the model, and you will be thorough with whatever molecules is given in your AP Chemistry exam. So thank you for joining in, and this was your Whisper lesson.